Good morning, everybody. Thank you for coming. My name is Fayira Sangare. Today I would like to present my research defense. The title of my research is Radio Frequency Energy Harvesting and Information Transfer Implementation in the Internet of Things. These are the contents of my presentation. It has two parts. The first one is a design of a dedicated single-channel radio frequency energy harvesting. In this part, I will explain the design, the hardware design I made, and also propose two optimization algorithms to maximize the energy transfer in a wireless sensor network. The second part is more general. It deals with the design of an ambient multi-channel radio frequency energy harvesting. Here too, I will propose a hardware design and also some optimization algorithm. And I will end the presentation by showing what kind of possible application can be applied. Do we need to close the door? Okay, all right. So first, let me get started with the introduction. As some of you already are well aware, by the year 2020, the next generation of networks, mobile networks, will be rolled out to address the growing user and business demand. The NGMN is a group of researchers, companies, and government bodies has designed the specifications for the 5G networks. It has created actually 8 use case families, like broadband access everywhere and the massive Internet of Things. Particularly in the massive IoT, this refers to the interconnection of devices, buildings, vehicles that can share data with one another and also be controlled remotely. And that enables the connection of several hardware, such as smart wearables, mobile phones, and sensor networks. So in the particular case of sensor networks, I would like to propose the use of all these frequency bands. Some of them can be used, for example, to wirelessly power the sensor networks, since there will be various frequency bands, and as well as it's going to be over a wide spectrum. So what I'm trying to address in this presentation is how we can safely or remotely transfer energy from a source to a sensor network, how we can store the energy and supply power continuously, and what kind of novel applications we can implement. So all this will be answered by the radio frequency energy harvesting. So radio frequency energy harvesting actually is a process of converting electromagnetic radiation to electricity. And the amount of harvested energy is given by this equation, where the received power is proportional to the antenna gains, the wavelength, the distance between the transmitter and receiver, and the transmit power. In comparison with other existing wireless energy transfer, electromagnetic radiation suffers from very low efficiency, not very low, but kind of low compared to inductive coupling and magnetic resonance coupling. But on the other hand, it has the advantage of operating in the far-field region. So we can use this radiation and remotely supply power to some devices without the need of having them very close to the source. Next, I will move into part 1, which is the design of a dedicated single-channel radio frequency energy harvesting. So let me start with section 1. This is a block diagram of a radio frequency energy harvesting system. It's made into 3 parts. The first part consists of a transmit antenna. This is a source, the radio frequency source. The second part is actually the receiver and converter. This is the harvester that receives the radio signals, convert them into a DC voltage, and supply it to an application or storage device. And there are 2 kinds of storage devices. One can be, actually it's power management, sorry. One is called harvest use. So whatever voltage we get from the harvester, we use that directly for the application. The second one is called harvest store use, where we store the amount of harvested voltage into a device and can use it later or on the spot for the application. So in this presentation, in this introduction, I will go into those 3 blocks: the transmitters, the harvester, and the power management structure. So about the energy harvesting sources, there are basically two kinds of sources. One is called dedicated. These are transmitters that are solely for the purpose of transmitting energy to, let's say, a wireless sensor network. So this can be used when we need predictable energy supply. However, it can be costly, and also the output of the transmitter has to be limited by regulations. So here I have a picture of a PowerCast transmitter that supplies radio frequency signals at a frequency of 915 megahertz to a sensor board. The other type of transmitters are called ambient. These are transmitters that are not originally made for power transfer. And there are two types of transmitters in this case. One is called ambient, static ambient, like the case of cell phone towers or TV towers, for example. The other one is called dynamic ambient, like, for example, a time-varying source like Wi-Fi router, for example, or users in a cognitive radio network. In this presentation, the first part of my research will deal with dedicated transmitter. The second part will be on ambient transmitters. The second block of the energy harvester is actually the second block of the system is the energy harvester. For this, I selected the hardware of a company called PowerCast. This is the evaluation board that is supplied. It comes with a chip. It's a proprietary chip from PowerCast that converts harvested radio frequency signals into a DC voltage. And this DC voltage can be stored in a supercapacitor or a battery, or can be used directly for an application. So besides this hardware, I also purchased some other equipment from the same company, PowerCast. So this equipment are shown here. First, we have the option of choosing two antennas. Actually, one is a dipole antenna, which is omnidirectional. The other one is a patch, which is directional. The power that is harvested by and converted by this board can be used to supply energy to a wireless sensor board. And the sensor board communicates with an access point shown here that connects to a computer and get the data from the sensor board. And additionally, we have a programmer that can be used to modify the behavior of the microcontroller of this sensor board. And this is a dedicated transmitter from PowerCast. Next, I will show. Actually, this energy harvester board has a default firmware setting, so it enables for a very short operation. This is a Vout output by the sensor by the energy harvester. It's a very short and intermittent power output. But my goal is to supply energy for the longest period of time to a sensor. So I made some modifications, such as removing a reset signal and implementing some power savings feature to reduce the energy consumption. So the third and last block of the energy harvesting system is the energy storage. So there are two ways, as I said earlier, to manage the power harvested. One is called harvest, store, use. One is called harvest, use. In this part one, I will only focus on harvest, store, use. And the energy that we will harvest can be stored in either supercapacitor or rechargeable battery. In my research, I focus on supercapacitors. The reason why is because basically they are between conventional capacitors and batteries and rechargeable batteries, but they have a higher energy density, and they can be recharged faster than the rechargeable battery, and they allow for many recharge cycles. So that's the advantage of having supercapacitor. But yes, it's this one. Actually, the other name is electrochemical capacitor. It's in the between. It's here, and it has to be chosen carefully because it needs to have a very low ESR, which stands for electrostatic equivalent series resistance, and also a very low leakage current. So for these reasons, I carefully selected a supercapacitor for a company called PowerStore, 5 farad, and these are the specifications of this supercapacitor. The next section is about the design of a dynamic control for radio frequency energy harvester with an unmanned charging vehicle. So the motivation for this research is to design a wireless sensor network that is charged wirelessly by a vehicle. And the energy that we get can be stored in a supercapacitor, and power savings can be implemented by firmware. So here is a picture of the mobile charge vehicle that travels through a path and charges its sensors remotely, and it contains a wireless charger. So beside the hardware, we need to find a dynamic solution that will select which sensor to charge, and in order to make sure that the sensors or boards never continue to operate, never fall below a working threshold. So dynamic programming allows us to solve this optimization problem. It's used in, I will explain a little bit more about dynamic programming in the next slide. And I will run simulations and compare with a naive solution to show the performance of this solution. Finally, at the end of this section, I will also show how I implemented this solution in a real hardware, and I have a video that is posted in YouTube. So as I said earlier, the goal is to find an optimal control of a charged vehicle that will travel to sensors and wirelessly maintain their energy level so that they can keep operating. So dynamic programming is used to solve this problem. It's used in situations where decisions have to be made into stages. And the goal is to minimize a certain cost, G, by taking an action, U. It's a decision variable. So our model has two features. The first one is a discrete time dynamic system where the next state, xk plus 1, is a function of the current state, the action to be taken, and some random noise. And the physical meaning for that can be, let's say, the energy that is used for processing the information and transmitting to the access point. Then we have a cost function where the cost that we occur by doing this algorithm is additive. So the terminal cost plus the cost of the previous steps. Because of the presence of this random variable wk, this cost cannot be determined exactly, so it has to be estimated. Next, I will show the dynamic control, the formulation of the dynamic control. We define a state, xk, where x stands for the remaining energy for one sensor at a specific time, k. So the goal, the action that has to be taken by the charge vehicle is to wirelessly charge. So the action is either 1, which means charge, or 0, which means not charge. And our dynamic system is of this form. The next state, xk plus 1, is a function is equal to the current state times a discharge factor, that is the discharge factor of the supercapacitor, plus the action to be taken, charge or no charge, and this is the charge efficiency factor when we charge the supercapacitor, and wk is just random noise or the energy used for processing and transmitting information. Our cost to go is quadratic. The first term stands for the remaining energy cost, and the other one stands for the charge, the cost that will occur when we actually do the charging. And the action that has to be taken is the one that minimizes this cost. The solution can be obtained by solving a Riccati equation. Then after that, we need to find the parameter that I explained earlier, the charge efficiency factor, the discharge factor, and the noise. So I ran some experiments by checking the behavior of the sensor board by putting its microcontroller to sleep every 65 seconds, 2 minutes, and roughly 4 minutes after each time after it transmits. And the optimal charge to sensor distance is about 18 centimeters, because below that our transmitter shuts off for safety reasons. And the goal is to make sure that each of the voltage across the supercapacitor has to be above a working threshold, because below this one, our microchip cannot operate. So this is a picture of the test setup. You have the powercast board, sensor board, the patch antenna. This is the transmitter, the 915 megahertz antenna. This is an example of the sensor board sending packets every couple of minutes. So we have a sleep time. These are the sensor data. So once I ran this experiment, I found the parameters alpha, beta, and W shown here. So I was able to run some simulations. So I ran some simulation with assuming two cases. One where we have the cost for charging that were lower and the cost for charging that is higher. And the setup is with 3 sensors. And by looking at the behavior here, I'm not taking into consideration the travel time or the time needed for selecting the sensor. So by just looking at the behavior, you can see that all 3 sensors are able to maintain their voltage value above a working threshold. And sensor 1, for example, is put to sleep every 1 minute, sensor 2 every couple of minutes, and sensor 3 has spent the most time sleeping. So I also compared this solution with a naive solution where we just select the one that has the lowest voltage value to
What's
make
the difference between these two? Just point out 2 or 3 differences.
Yes, actually, about these two graphs, they're basically the same, actually. So,
basically the same?
yes.
Or identical?
Not exactly identical, but similar. They share similar behavior. Well, looking at the voltage here, they look pretty much the same. I don't see a big difference.
No big difference? Or are they identical?
They look identical. Kind of paper is different? Oh, okay. Okay. Okay.
Well, tell us what would be different. I mean, what would be different? What would you see that looks like if these were the right plots? What's the difference in constants? Does it make any impact?
Yeah, the goal is to make sure that all the three sensors are able to operate right and not fall into a below the working threshold.
I think in the paper, if I remember correctly, okay, and that will mention kind of order like this. Who mentioned chapter? I remember that. You need to see the details for that. And in the paper, you briefly explain for that. In the P-value, potential value, resolution knowledge one. And this picture probably has some copy and paste problem.
Yeah, but in the published paper, the behavior is not it's not identical, of course, but both of the scenarios make sure that our sensors are able to work above the working threshold. So that is basically the goal of using this dynamic solution. And I also made a comparison with a naive solution where you have the three sensors with the dynamic solution in blue and the one with the naive solution in red. As you can see, for sensor 1 and 2, our dynamic solution the average is better than the naive solution. And also the order in which the sensors are selected is consistent. So it can be used when we need a fixed path planning, for example. And in my dissertation, I also showed how the average, which order the sensors are selected. Finally, if there's no question, I will move into the last slide. I implemented this solution in robots. The first one was done by some undergraduate students that I supervised a couple of years ago. The second one was done by me, where I use an iRobot with 3 sensors. And I can play a short video where we have
Start.
The iRobot is the rocket server how to charges, and then travel back. So the next section is it's a broader scope of this dynamic control. In this case, we will take into consideration the path planning and the scheduling. So here the goal is to model a mobile energy station. So this is a broader scope than the charge vehicle. So it can be any mobile charger that would travel through a pre-planned path. And the background is taken from research from these 2 teams. One of them focused on environmental energy harvesting. The other one did not have a path planning. And in this research, I used an MDP-based joint optimization problem for both path planning and mobile charging scheduling for the mobile energy station. So here the mobile energy station decides which path it will travel, and also it decides which subset of sensor to charge before actually going there and charge them. So this is our system model. We have K number of sensors. Okay, and W is the energy that is consumed by a specific sensor to transmit D number of packets. So it's a function of the number of packets transmitted. And the energy level storage of the the energy level of the storage device has to be less than the maximum energy that can be stored. So it is basically the previous energy storage at the previous step plus the energy received by the mobile energy station minus the energy used for transmission. The path chosen by the MES is a PT, and the MES can only charge the sensor when it is at this distance. So this is a problem formulation. As I said earlier, in this case, the goal is to make sure that each sensor can send data packets by minimizing the data loss. Data loss is given by L, where D is the number of received packets, and this is the energy that is used to transmit the number of packets. So just the inverse function. And the payoff is just the average of the data loss over the length of each time period where the mobile energy station has to go and travel and charge the sensor. So the goal is to minimize the long-term discounted data loss during trips where gamma is a discount factor. Before doing the joint optimization, I made some models, just like I did for the previous section, where I modeled the charge and discharge. Here you can see, I didn't show the distance, but the closer the distance, the higher, the faster the charge. And this is the actually power received by any capacitor. So it's a standard equation where this first voltage is a voltage that is received after a delta t duration of charge. This is the one that is consumed by processing and transmitting information. And this is the one before the actual time where we start doing the charging. Similarly, for the discharge, I ran two experiments. One where the microcontroller of the sensor board is always communicating, so it's in active mode. And when it is in sleep mode, you can see that the slope here is steeper. So it means that when the microcontroller is communicating, it's consuming more energy. So and this is a working threshold, 2.45 volts. So here I formulate an MDP, a macro decision process for both the path planning and charge schedule. The state space is a finite finite set actually, where each state psi t belongs to this state space, and it is actually the voltage level of one sensor and the data transmitted at a certain time. The action to be taken is choosing a path and which subset of sensor to charge. So it's a tuple of PT and ST. And the state transition function is given by T, where by taking action, starting with state psi t and taking action AT, the system falls to the next state is psi t plus 1. So this is the joint optimization results. Actually, for minimizing the data loss that I showed earlier, this is the goal of this optimization. Our MES has to evaluate before going and charge the current data loss and future data loss that could occur by taking a certain action. And the payoff, which is the data loss that could occur by taking a certain action, is given by omega bar t. And the value function is just the current data loss shown here, and the discounted future data loss that could happen by taking action A. And V star is just the optimal value function that would minimize our data loss. So by taking the optimal action A star, we have the optimal policy that we select the correct path and correct subset of sensor to charge. So these are the simulation results. My setup was of 3 sensor boards shown here, 1, 2, and 3. We have a circular path, that is path 1, where the mobile energy station can go and try and charge all 3 sensors. And we assume that each sensor sends data packets randomly. So the MES has to choose which path and which subset of sensors to charge according to the state of the system. So I ran simulations. The first case, for example, we choose a time period of 10 minutes. So we want to verify the probability of this mobile energy station to charge sensor 1 assuming the voltage level of the sensor. Obviously, when the sensor board has enough voltage, enough power, the mobile energy station will not go and charge it. But when the voltage level is very low, I mean, getting close to the working threshold, the probability to be selected is very high. And on the other hand, when the data packet is becoming higher, it means that the sensor board is spending more energy, right? So the probability to be selected goes higher too. I also run another simulation case where the time duration is 20 minutes. So as I said earlier, for path 1 is 5 minutes in total. So by choosing this path, we are able to charge at least 2 sensors, right? 2 sensor boards. So this is the probability of this MES to choose path 1 and charge sensor 1 and sensor 2. So here, when the voltage level across sensor 1 is high, the mobile energy station obviously will not go and charge it. So it will just travel and charge sensor 2 and sensor 3. If the data packet sent by sensor 1 is high, obviously it will charge it, right? And if the voltage level across the supercapacitor of this sensor is getting low, also the probability to be selected and charged is going to be high. Finally, the last simulations I made were to compare this joint optimization policy with another sequential charge policy, where we divide the time slot exactly into 3 parts, where each part belongs to charging 1 sensor. So here I compare the data loss versus the duration of time. So if you have a very short duration of time, obviously our joint optimization policy will be better. So we will minimize the data loss. But if we have more time, sequential charging will divide the time period into 3 parts, so it will have more time to charge all the sensors. So the data loss will be basically almost the same. So our joint optimization policy is better if it's used for data loss sensitive applications. I also compared both policies by checking the amount of data loss compared to the arrived data packets. So for low data packets, they are basically the same sequential charging and our joint optimization policy. But when the data packets arrival is getting higher, our joint optimization policy is better. So these are the 4 simulations I run for these experiments. So the next part is the design of ambient multi-channel radio frequency energy harvesting. So the goal of this section is to design a multi-channel radio frequency energy harvesting, design the correct hardware, and also formulate some optimization policies. So let me start with the hardware that I used for this section. So the goal, as I said earlier, is to design a multi-channel ambient radio frequency energy harvester that can get energy from ambient radio frequency signals. So I selected some hardware prototypes, some antennas. Also did a brief RF survey to make sure that we can harvest enough radio signals. So I also made some investigation to compare how much power density we have, depending on what energy source we have. So basically, the amount of power density is very low. The maximum we have here, for example, is only 2 milliwatt per square meter. So it's a very challenging topic. So the hardware I selected for my experiments is another PowerCast board. It's a P21XX CSR evaluation board. It supports 6 frequency bands, shown here: GSM, ISM USA, and Wi-Fi. And this harvester board is just like the previous one. It harvests radio frequency signals converted to DC voltage that can be used to supply power to a sensor board or any low power device. I also made sure that I also measured the power received by this board in order to find the bare minimum power needed to operate this board. So it is about -10 dBm at a distance of 2 meters. Next, I chose some antennas and I ran some tests to see if I can harvest signals and turn on this board. So I purchased some antennas from Texas Instruments Tower Glass, some Wi-Fi antennas, and some GSM antennas also. And I did some tests using an EMC analyzer in the lab. And these are just snapshots of the test setups. The summary is in the next slide. Here you can see that the recovered energy or power is not sufficient, for example, if we need to use it in the harvest use application where whatever we harvest, we use it. So this is the minimum power that we need to power this board. However, there are ways, for example, to optimize the power that we harvest. For example, we can try to find a way to boost these ambient radio signals. One way is to make sure that we use it in a period where we have plenty of signals. Like, for example, during the day, if we're close to a radio tower, and we can also make sure that we're very close to the transmitter. The other way is to design a better circuit than the one I showed you earlier, and a better antenna, which is outside the scope of my research. And the other way is also to modify, for example, let's say Wi-Fi, because Wi-Fi can be legally modified and to deliver power. So just for the sake of running experiments, I purchased a Wi-Fi router. I modified the firmware, and I used the same board and created a home group. I will show you a short video here. So I had a setup of 2 computers and a modified router. I modified the firmware so that it can transmit at the maximum power. And this is a PowerCast board. So I just copied some files from one computer to the other, shown here. And you can see that the voltage is harvested by this PowerCast board and is able to turn on this LED. And once the LED turns on, it means that we have enough power to supply to the sensor board. So in the next 2 slides, I will show, I decided to focus on general ambient signals and try to relax the problem and focus on a harvest use situation and a harvester use situation. The first one, I used the SWIFT, which is simultaneous wireless information and power transfer, using a harvest use method. So in this case, as you know, with SWIFT, we can use both, the same wireless signal to transfer energy and also exchange information at the same time. However, it's very difficult to achieve because the amount of information is a function of the variation or entropy rate, and the energy just the square value of the peak, so it cannot be optimized at the same time. But in the second section of this presentation, I will show an opportunistic sensing strategy that can be used to implement the SWIFT. The other one is harvester use with cognitive radio. Cognitive radio is an intelligent radio that can be programmed and configured dynamically. So it can scan and select which kind of channels are available in the spectrum. And with that, it can allow for concurrent wireless communication. But I can also use that one to search for radio frequency signals for harvesting and also to search for channels for communication at the same time for a harvester use scenario. And for this scenario, I purchased some hardware and I put them together. I will show in the last section of my presentation how the performance of this setup. So this is a picture of the setup. It's made of, first, as I said earlier, it's very difficult to harvest ambient and radio frequency signals if I don't do those modifications that I explained earlier. For this case, for this reason, I just simulated the signals by using a USRP controlled by a LabVIEW program in a computer. Here we have the transmit antenna. Then whatever signals are transmitted can be received by any of these 6 antennas. And the signals are supplied to the PowerCast evaluation board. And the PowerCast evaluation board that converts the harvested signals into a DC voltage to operate the sensor board. So this can be a sensor board or any low power device. And because we have a cognitive radio, we need to have an agent or cognitive agent that can be intelligent enough to scan the channels and choose which one, because the PowerCast board doesn't have this brain in the setup. So I purchased some equipment made by an Arduino board that contains a microprocessor and a multiplexer that can switch and select one channel at a time. The channel that has the highest energy can be used to supply power to the PowerCast board. Then whatever data we have, we are able to send from this sensor board can be received by the access point. And later, at the end of this presentation, I will show you a demonstration. The Arduino can be powered by the computer and can be powered by the board, but I'm used to power by the computer because this is intermittent, right? The voltage output by the harvest is intermittent, so I just supply power by the computer from a USB board, from a USB cable. I'm sorry. So next, I will show the design of a sensing strategy for a harvest use scenario. So I will use Swift that I explained earlier, where the harvested energy is used to operate a low power device. So the goal is to design an ambient multi-channel Swift that can select one channel that has the highest probability of being occupied, that we can use to harvest ambient energy. And at the same time, you need to select one channel that is free, that we can use and access and send information for opportunistic transmission. And for the simulation, I use a specification of the PowerCast board. So this is our system model. We have n number of channels, each with bandwidth Bi. The received energy is just proportional to the antenna gain, like I showed you earlier in the presentation. The received power spectral density is just a ratio of the received energy and the bandwidth. And each of these channels follow a discrete time Markov process with m number of states. So here I define the number of bits transmitted per channel as R, where G is the gain of a specific channel, and sigma square is the noise. This is for the information transfer. For the energy that can be received is given by E, where phi is an energy harvesting efficiency, tau is just the time duration, B is the bandwidth I explained earlier, and rho is the power spectral density. So this has to be higher than the energy transmitted and the energy used for processing. Because we in the situation of an ambient radio frequency scenario, we cannot directly know the state of each channel. So here we formulate it as a partially observable Markov decision process, where the action to be taken either is one channel that has to be chosen for energy harvesting, and the other one that has to be chosen for information transfer. And the goal is to maximize the utility, which is the number of bits shown here, divided by the energy harvesting. So it's the number of bits transmitted per energy harvesting time. However, to solve this, the optimal policy to maximize this R requires to solve this POMDP. So it's kind of very difficult to achieve. So I propose some suboptimal strategies instead, which are greedy-based. In the next slide, I will explain what the greedy-based strategies are. So first, I define the probability that one channel, J, is in occupied state as omega J. So our energy harvester has to jointly search for one channel to harvest energy and one channel to transmit data. So the probability that one channel J is in occupied state is given by this one, where omega J, as I said earlier, is the probability that the channel is in occupied state, and it's going to stay in occupied state. And the other probability is the probability that the channel was not in occupied state, it was idle, but it's going to transition into occupied state at the next decision level. And at the same time, we need to find the probability that one channel is also free that we can use concurrently to transmit information. So it's just 1 minus the probability that one channel is in occupied state. So next, I will define two greedy-based opportunistic sensing strategy. One is called sequential. The other one is concurrent. So this is the first greedy-based strategy. It's called sequential sensing. In this case, we sense one channel for harvesting energy, because whatever we harvest, we need to use it for transmitting information. We need to use that energy to transmit information. So that channel is the one that has the highest chance of being occupied. This is the energy. So if you confirm that the channel J hat is occupied, then we need to find one channel that is free. It's just 1 minus the probability of being occupied that we can use to transmit information. However, if you find that J hat, we thought that it's going to be occupied, actually is in fact idle, so we know that we have one channel that is idle that we can use for transmission. And then we need to sense another channel that we can use to harvest energy. So it's 2 steps. Either we find the first channel that is occupied to harvest energy and find the next one for transmission, or we're unlucky, the channel was idle, but we have at least one channel that we know that is for sure idle, and we search another one for harvesting energy. The other greedy-based strategy is called concurrent sensing. In this case, we need to find 2 channels, I and J, that are concurrently in different states. One has to be occupied, one has to be idle. So here, one channel I is idle, and channel J is occupied, or channel I is occupied and channel J is idle. The combination that has the highest utility, that maximizes the utility, is the one that is chosen. But if you find that both channels are idle or both channels are occupied, then we have 0. So I ran some simulations by selecting the probability of being occupied, omega j 0.8, and the other one, actually that's I 0.2, idle, I'm sorry, and the random harvesting efficiency. So I compared the performance of my algorithm, sequential sensing, with concurrent sensing. By comparing the achievable data rate, we can see that it's way better. And also even comparing with random sensing, where we randomly select some channels for harvesting energy. So these are simulations for this algorithm. Lastly, I will explore the cognitive radio for a harvest, store, use scenario. So here the motivation are first to design a harvest, store, use system for jointly harvesting energy and accessing a channel in a cognitive radio environment. So I use a multi-channel powercast board where we select 2 channels. We have a combination of 36, right, because we have 6 channels, but we can only select 2 at a time, and they have to be different. So it's going to be 30 combinations. So we use a multi-arm bandit problem to formulate this algorithm. So this is multi-arm bandit problem takes in name from slot machine, where we pull an arm and get some reward. So it's using a sequential decision making. Actually, it was originally designed for the motivation was like to study bandit problem from clinical trials, where we have different treatments available for a certain disease, and we try to decide which treatment is better for which patient. So the goal is to balance. Yeah. So the goal is to balance the action that perform well. I'm sorry, and also explore some other opportunities. So if you have a good channel, we can keep exploiting it. But at the same time, we have to keep in mind that maybe there is a better opportunity somewhere else. So it's a way to balance both exploration and exploitation. And I evaluate the performance of this algorithm with a greedy-based algorithm. So there are several multi-arm bandit types. All of them define a sequence pair of state and some reward associated with each pair. The first one is stochastic, where we have an unknown reward distribution that is associated with each arm. The other one is called adversarial. We play an unknown game against one opponent, so the player only knows its own payoff. The third and last one is called Markovian, where each arm is associated with a certain with k microprocesses, and the reward is run from a distribution. So here, in this case, I focus into the Markovian multi-arm bandit, where the control actions are two. Either 0, that is freeze, we don't do anything, or 1, and we get a certain reward. So when we select one combination out of the 30 that I showed you earlier, we get a certain reward, and all these other channels are frozen. Next, this is the reward. I define a global decision epoch, where pi is the number of times we play the machine or arm or the channel, or channel combination. The reward is given by this equation. So we have a discount factor here that accounts for a low value of discount factor of gamma means that we favor the exploitation, so we keep using it, and the high value means we favor the exploration. And the goal is to maximize the reward. John Gittins has shown that the optimal policy can be achieved by playing the arm that has the highest Gittins index, which is basically the ratio of the expected total reward, expected total discounted reward, and the expected total time, discounted time. And each arm, the best arm is the one that has the highest Gittins index and can be played up to a certain stopping time. If you find that the Gittins index is smaller than it was before, then we stop and we try to explore another opportunity. And this is the arm that has to be selected. It's a combination of 2 out of 30 combinations. This is a joint reward. So we're trying to maximize both the data transmission, shown here, the transmission power and channel gain, and also the energy harvesting. So the harvested energy minus a certain cost. This is the cost that is used for transmission or processing. And to evaluate the performance of this algorithm, we need to find a way to do so. And the way to do so is to evaluate the regret. This is basically what would have happened had we selected the best combination all the time. So obviously, we have to find the best combination that are able to achieve the highest reward so that we can keep playing that arm. But but we don't know the future, right? So we have to just do the estimation. So I ran some simulations by comparing this Gittins strategy and the epsilon greedy. So here we have a plot of 3 channel combinations, channel 1, 2, and 3, by playing the Gittins index strategy and the epsilon greedy. So as you can see, the Gittins index selects the optimal channel most of the time as compared to the epsilon greedy. And here we can see the plot of each of the Gittins index at each decision epoch.
And why is the third one jumping around so much?
That's channel 3, Gittins index. That's the index that I calculated each time. Actually, the reward follows, it's because of the distribution of the, both follow a distribution, the Rayleigh distribution.
So why isn't channel 2 jumping around like that?
No, because channel 2, channel 3 is the one that gives the optimal, the highest Gittins index compared to channel 2. That's the optimal channel. So it has the highest Gittins index on this scenario, on this test.
So the radio that is channel 3 is varying in power a lot?
All of them are varying in power over time, but the combination of actually it's not channel 3, it's a combination of 2 channels. So each one of them has a certain parameter from the Rayleigh distribution. So the combination of 2 channels gives channel 3 has the highest distribution compared to the other 2.
I still have no idea what's going on.
Okay, so I will go back. So the Markovian multi-arm bandit, sorry. Here we have a reward that is run from a distribution. And it's because we using wireless channels, I use a Rayleigh distribution that accounts for path loss and reflection and all this kind of defects that can reduce the strength of the signal.
You have 3 broadcasting antennas, 2 and 3.
No, you have 6 antennas, right?
You have 6 antennas.
Yes.
1, 2, 3, 4, 5, 6.
Yes.
And all of them are following a Rayleigh distribution.
Yes.
of power output
Yes, power and information transfer.
that is changing every second.
Over time. It's not. It doesn't have to be. Yeah.
It's this kind of pseudo kind of static. Between one temporal static, between there is a really distribution.
Okay, so that, and so you're going to sense for the first microsecond or so, and then it's going to be the static for your time period.
But
Yeah.
the point is that okay, even though they follow this one, the meaning is different. Some is closer, some is far away, so the meaning will be different.
And the optimal one, is that always going to be the optimal, or is it going to be switching all the time?
It's not switching, but in that case it's not. In the sense that okay, we are not changing to this one, but later okay, this is a test to show that okay, we can switch into the other. Yeah. Can you put the figure?
Does he have a figure of the actual power of the 6 channels as a function of time?
Yes, it's not the power, but the Gittins index. The index.
So the Gitz index is a statistic.
Yes, it's a ratio of the reward, the total discounted reward, and the total discounted time.
Maybe I can, this figure should be kind of unique in the sense that okay, you see the reason why it's fluctuation is because never get sample. So the first one is the blue line, get sample, so it's going to be stable, and then okay, this kind of green line is basically because I never have sample for that, so it can be totally influenced by this. I mean the current channel or this kind of the other nature. But you see, as time 15 times you get sample, and then it becomes stable because you already have sample. But if the red line is not get sample, later, I mean, I mean, never get sample, something like that, and so that it will kind of fluctuate again until it gets sample, and then it will kind of that. So these are beginning, okay, this red line is basically trying to haven't get any sample, so that's really kind of fluctuate.
So you're saying it's kind of lack of information is
Lack of information, yeah. So that is random until there are some opportunities that it can get the point, and then it can be stable, and then continue to get update. So that's reason I think I suggest you to remove this one. Anyway, but
It's just to show that.
you can show that okay. You see that interoperability is nothing but I give you a certain probability to try this one. But this index is depending on history and started by itself, so that I give the optimal. I mean, under that criteria, what is the kind of probability to explore the other? Interoperability is just anything I just explore certain probability. But that one, depending on the past experience, then I will try a certain probability.
Well, maybe it's useful to leave it in the dissertation to explain why this is happening.
Sure.
And how would you do if we just said, oh, always use channel 3?
Because sometimes channel 3, because we're trying to balance the exploration, use the same channel that has the highest index. So in this case, we didn't have the channel 3 was not optimal at the next decision because the Gittins index was not higher than it was before. So we switched to another channel. That was perfect.
Measure one channel
At the time. Yes.
Yeah, that is the multi-hypothesis problem assumption. You cannot play the two problem things together.
Actually, it's a combination of channels. It's not one channel, actually. It's a combination of channels. It's a combination because we have 6 channels for energy harvesting and 6 channels for transmission.
So when you say channel 1, you really mean
2.
pair
A pair of channels.
So,
Yeah.
So totally you have 36.
Because you have 6
channels A, channels B, and channels C.
Yeah,
I think,
yeah.
I think harvesting and transmission, this can pair. So totally we have 6 by 6, so 36.
30,
Or
yeah.
maybe due to the harvesting side, I mean assumption, we have 30. Because we cannot simultaneously harvesting and transmission at the same time. So maybe minus 6. 33 minus 6, 30.
30.
Now we have 30 channels.
Yes, 30 channels. We have 30 pairs.
Physical channel, but due to the transmission receiver.
It seems it's not that it's not get sampled. It's changing because we get sampled so many times. So that's why when you draw it, it won't be flat. You see, if you look at the left, right, if you look at the blue, so you see channel 1 only being checked. Well, maybe I'm wrong.
Yeah, no. So finally, which one is the one you select? Channel 1, 2, 3,
3.
Oh, then you are right. Because the other have no opportunity to explore, so it keeps the result over there. This is the previous sample. And then the channel 3, because the representation, so it sample all the time. And also it's always better than the other. So the other have no opportunity. And that's the obvious.
Yeah, I think channel 3 been sampled so many times. That's why when we draw
We
the
keep-
value, it becomes like, because the sample interval is very short. So if you only sample once, if you look at channel 1, right, it only done once in the middle. So that's why you see it's only change value once in the middle. Now for channel 2, it sends bunch of them at the beginning. That's why the tricky thing. But it's actually draw multiple sensor results continuously. That's why you see this. And then for channel 3, he sends so many times and he draws them continuously. That's why you see all this. I think this match actually.
Yeah, then you're right. You're right. That's a better resolution.
In chapter 7, does it give a definition for PDF for other distribution?
No, I don't give this definition. Well, I just give the PDF of it, but I don't explain all the details.
You give the PDF first.
I have to.
In chapter 7, it's in there?
Yes, it's yeah. But I didn't go into the details of.
Yeah, maybe in the presentation you are clear about it.
So finally, I run some tests using this cognitive radio environment. So here I will show by using the multi-arm bandit.
So now you have the 915 megahertz antenna. The LED is blinking and the voltage goes up, then goes down when the LED blinks. So I will stop and switch to 879 antenna, megahertz antenna. LED blinks and goes away, the voltage goes up and down.
Exploration, it will pick up the highest channel and start to harvest energy. So you see it's going up to 0.7, it means that the LED is blinking and outputting voltage to the sensor board. Then I also modify another antenna and verify that it's consistent with each antenna. The system, the algorithm is able to catch which antenna, which signal is the highest to harvest energy and supply power to the sensor board.
So LEDs blink.
Finally, I will show some of the potential future work that can be done. If you have noticed in this presentation, I only focused on fixed devices. But in the case of you have IoT devices or phones, anything that are moving, our joint optimization policies may not be the best. So for that, I suggest to use massive MIMO, multiple input, multiple output antennas. There are two kinds, like point-to-point MIMO, where you have two devices, multiple antennas, and multi-user, where you have one base station with multiple antennas. So this is the one I suggest, and there's also research and hardware platform that can be used to implement this massive MIMO for moving devices. And lastly, okay. I think there's a software in the background that is preventing this from moving. From the Swift architecture I showed earlier in this presentation, give us called co-located. It allows me to open it. Okay. Okay. So these are kind of other architectures that can be considered in the design of a multi-channel ambient energy harvester. So this can be considered in the next work. And also, if you remember, in my hardware, I had only 6 antennas for harvesting, but only 1 for transmission. So maybe we can also modify the hardware, find a different hardware to also harvest energy. I mean, to have 6 other output for information transfer. So finally, because this is the one that I proposed. So in conclusion, I in this research, I have designed an RF energy harvester for the Internet of Things from dedicated sources with a single channel, and also from multiple channels by harvesting energy from ambient sources. I also designed some optimization algorithm to select which channel can be used for in the first section, just from dedicated sources, the other one from ambient. And I showed the proof of concept in videos, and these are the potential works that can be done in this research. So thank you very much for your time and consideration. And, if you have any question, I welcome them.